It has a lot of applications in inferential statistics. Especially, it has brought in a lot of concepts into the world of inferential statistics because of a big assumption that has come, or a big conclusion that has come in terms of the pattern in the data, especially when you want to compare the means of a population. The mean of a population, if you want to make some kind of conclusions or inferences regarding the mean of a population, we are resorting to the central limit theorem. What it is saying is, see, if especially if we are working with sample of data and we want to make some kind of inference about the population, like the mean of a population, we want to compare the mean of a population with something, or we want to say whether the average height of males is greater than the average height of females. Whenever we want to make such kind of conclusions in statistics, because any statistical calculation which we have to do, apart from calculation, there is an inference or a conclusion angle associated with it. And to make those conclusions more and more comfortable, the central limit theorem is really helping us out with. What it is saying is, if you look at the various random variables, x1, x2, x3, if you are thinking of the various random variables, which are nothing but, let's say you are talking about a data. Like, let me just show it to you. I'm taking a data. Let's say this is, I'm taking some values randomly between 51 to 200. Some numbers I'm taking randomly. So let's assume there is a data whose values are lying between 51 to 200. Now what I'm doing, I'm taking a sample. Let's assume I have taken 100 items, out of that some population, or probably let's talk about the heights of people. Randomly I am assuming that the heights of the people are between, let's say, 140 centimeters to 200 centimeters. Any person I am taking at random, his height would be somewhere in that region. So like that, what I am doing, some 100 people's height, on a random basis, I have picked up some people and I have measured their heights, right? And I have taken their average. I don't know what the distribution the data is. The data can be either a normal distribution or a uniform distribution or whatever it is. What I will do is, out of that entire population, I have taken a sample of size some 100 people, and let's say I am measuring their average height. Now what is their average height? Let's say I got here 170.73. Okay, I will note down all these sample heights, 170.73. Then another random sample, some other sample came out, and for that sample the average came out as 169.37. Another 169.21, like that, 171.08, like that I am getting various averages, right? 169.37. So it's like you are randomly selecting some 100 people, right? Some 100 people you are randomly selecting and you are measuring their average height, right? In some cases the number is much lesser, in some cases the number is much higher, right? Like this you can repeat so many times. You can take some 100 people and measure their heights, and this is how you can document all their height, all their average heights. We are not documenting their heights, we are documenting the average. Correct? Now, what the central limit theorem is saying is, when you take a sample of some size n and you look at their sample mean, this is their sample mean, these are their sample means, sample average. What it says is the sample mean also keeps changing because your sample is changing. The sample mean is also changing. But what they say is this sample mean actually follows a normal distribution. This sample mean, because it is changing, first of all, it's a random variable, not the data. I'm talking about the mean itself. The mean itself is a random variable because it is changing. And what the central limit theorem has come out is, this sample means they follow a normal distribution. Whatever is the distribution of this data, doesn't matter. The sample means will follow a normal distribution with the mean. Now, if you just want to check out, I can look at the skewness in this. Skewness should be 0 for a normal distribution. Okay, I'll check out for the skewness. It will be very close to 0 itself. Probably if I take a few more like this, we may find that the skewness will be very close to 0, which is an indication of normal distribution itself. So what it says is, in case of a normal distribution, in case of any distribution, when I look at the sample means will follow a normal distribution with a mean. Now, what is the mean of this? The mean of this is something. The mean of this will approach the population mean. The whole population, whatever we are talking of, it will be more equal to that population. It will approach that population mean with a variance equal to sigma squared by n. Sigma squared is, from here I can take the standard deviation squared, or the variance I can take, or standard deviation is sigma by root n. So I'll take standard deviation of this, so 18 or something, by root n. Root n is root 100. 100 is our sample size which we have taken in this case. So I will take it as root 100. Now what it says is, when I go with it, the sample mean, these are all the sample means. The sample mean will approach the population mean with a variance of sigma squared by n, or with a standard deviation of sigma by root n. Which means this one. 100 sample of size 100. It's like the heights of 100 different people on a random basis. So you may pick this 100 set of people. I may pick this 100 set of people. From the population is same. Population could be some 1 lakh people. Out of that I am pulling out some 100 people. So the actual members will be different. The actual members of that will be different, but the size will be the same. See, why we are thinking of this? Using the sample, we want to make some prediction about the population. See, basically, I don't want to go to 1 lakh people and measure their heights. Right? So, I'm just trying out some 100 people and measuring their heights. I got some number. But that may not be the same of 1 lakh. The average height of the some 100 people may or may not reflect the 1 lakh people. So what we are saying is, probably you do one more 100. You do one more 100. You do one more 100. Now, if every one of us do 100, again there is a big cost to it. Now, what the central limit theorem has come out with is, if so many of you are doing some 100 samples kind of stuff and measuring the averages, each one will get a different number. Like you got 170, I got 169, someone else got 169.21. These are the averages. Now, without doing all this, what it is saying is, you do it only for one sample. Probably for one sample you do it. You do it for one sample, and so your population average will be something similar to your sample average plus or minus some interval around it. Right? It's basically, if you see here, the averages are more or less in a small region. Even if all of us are taking different 100 people, the averages are in a small region only. They are not widely varying. So that is what central limit theorem could prove, saying even if you do it with one sample, right, you build an interval around that sample. So the population mean will be